Hello, folks, and welcome back to another episode of Long Branch Never. In our previous episode, we coded our first Hello World app in 6809 assembler for the TRS-80 color computer. Today, we'll improve upon that app using text data strings stored in memory locations and demonstrating how we can use loops to iterate through those data strings to make printing text to our video screen much easier and more efficient. It's going to be much simpler than the manual method we used in our last episode. If you've coded in BASIC, this approach will be similar to how you may have used data statements in your BASIC code. Okay, before we get started on improving our code, I want to do a quick review of some of the topics we covered in our last episode. We had demonstrated how to use the A accumulator and X index register for loading data into the CPU and storing that data on the text video screen. We also covered immediate, extended, and direct addressing modes. In addition, we covered a few different notations and number formats for loading our A register with data. Now, I want to make some clarifications on the addressing modes we used. At one point in the last episode, I mistakenly implied that the $sign was used for extended addressing. It doesn't mean that at all. The only thing the $sign means is that we are using hexadecimal notation for that particular number. We will often see the $sign with extended addressing, but that alone does not mean that we are in extended addressing mode. And I'm just going to show you a couple examples of that real quick. So I've pulled up some code that we worked on in the last episode, and it looks slightly different than what we had finished with. I still have some of the manual addressing in here that we had started the episode with. I wanted to illustrate some points around the addressing modes, the number formats, and the notation that we used, as well as the start and end compiler directives that we had used in the code. We didn't have a chance to get to those in the last episode, so I wanted to follow up in this episode. So I'm going to go ahead and compile this as is and send the output to our VCC emulator, just so you can see where we left off in our last episode. So to do that, we open up our command window, we navigate to our desktop folder, and then to our 6809 assembly code folder. And we see that we have our sem.bat file still there and the hello source code as well. So I'm going to go ahead and compile that. And again, leaving off the extensions on these files. And our target is going to be VCC. And there we go. It's our Hello World app, just as we had left it last week. And what I want to do is just take a look at the compiled code and the machine language in particular, so we can take a look again as to how this is actually compiling. And again, using the org statement to indicate that we wanted to start our executable code or start our code compiling at memory address 4000. And as you can see here in this leftmost column, we're starting off in memory address 4000. And then our first statement, first machine code that was compiled is this 86 byte here, hexadecimal 86, which is our load A immediate mode. And then the operand that follows that is the 48 hexadecimal, which is the representation for our 72 decimal here. And as you remember, the rest of the code pretty much follows that same pattern. So I'm going to go ahead and go into our source code here, and we're going to modify this a little bit because, again, I wanted to show you the difference between our immediate mode, our direct mode, and our extended mode. So to do that, what I'm going to do is make an insert here. I'm going to add a line, and I'm going to go ahead and add a couple commands here that is going to show the difference between the addressing modes. So we're going to do a load A, and the first one I'm going to do is $50. And if you remember from the last episode, again, the $sign indicating that we are doing hexadecimal notation, and because there's no pound sign in front of that, this is going to be direct mode. And the reason why it's direct mode is because we are only including 1 byte in the operand field. And that right there will by default go to direct mode. So what we can do with this is we can expand upon this a little further. We're going to do another load A here. And this time I'm going to do $0050. Now, at first glance, you would think that this would be extended mode, and under normal circumstances, it typically would. Now, what's happening here, though, is we are actually using direct mode, and the reason for that is because the 00 is the direct page value, and the compiler actually knows that. It's 0 by default. We haven't modified it. We haven't used setDP to change it. We haven't transferred any other value into the DP register. So by default, it's 00. So this is actually going to compile as direct mode and not extended mode. However, if I were to change it once again, and we go to $0150, this now is going to be extended mode. And the reason for that is because we have 2 bytes in our operand. The 01 is our first byte, which is indicating which page of memory. And again, if you remember, if you break out the 64K of the color computer into 256 pages, you have 256 bytes in each page. So you have 00 through FF, and this is actually 01, indicating that it's technically the second page. 00 would be the first page. So this actually would compile to extended addressing. So what I'm going to do is I'm going to go ahead and save this and compile it as is and show you what I'm talking about. Now, this isn't going to modify the output of our Hello World app at all, because what's going to happen is we're going to come down after we store the H on the screen, and we're going to load A with the value of what's stored in memory address 50, 0050, hexadecimal. Then what it's going to do is do the same thing. This is essentially the same exact command, because again, this is going to be direct page. And then this one here, the next one down, is going to load the memory, load A register with the value of what is in memory address hexadecimal 0150. But if we go down to the next line, it's going to replace that with loading A register with the decimal value of 69 or RE character. So it's not going to change a thing. We're just going through a bunch of unnecessary steps to illustrate this. So again, I'm just going to save this, which we just did, and we're going to go ahead and compile it. And I'm just going to let it go. Well, actually, we'll do to VCC so you can see that it's the same exact thing. So we'll go ahead and get rid of this. And now I'm going to pull up the compiled output again, and we're going to take a closer look at this. So again, here's our first statement showing that we're load A immediate mode with a hexadecimal value of 48. Then the B7 is the store A into memory address 0500. The leading 0 is just left off here. And then the next statement down, we have a 96 instead of an 86. This 96 is indicative, is the machine language compiled byte for loading A with direct mode. And the reason why I know that is because I have a handy manual here. We'll go up to the beginning of this so I can show you the title screen of this. This is the Motorola 6809 and Hitachi 6309 Programmer's Reference Manual. And this was written, put together by Darren Atkinson. Now that name may sound familiar to some folks in the community, as it should, because Darren is the individual who is responsible for the Coco SDC. Ed Snyder sells them, and he's done some work on them, but Darren was the one that originally created it. So Darren's done an awful lot for the community. Not sure if he's still active, but this is something that I think, this reference guide is something that I think that anyone that codes in 6809 assembly language references. So I highly suggest that you do get a copy of this. There's a link to it down in the show notes below, and we're going to be using this quite a bit moving forward. So let's go ahead and take a look at our load A command. And as you can see, this is indexed very nicely. We have all our 6809 assembly code opcodes here for reference, and it also has the 6309 opcodes as well. And they're actually, it's really easy to tell which ones are which, and I'll show you that in a second. So I'm going to scroll down, and we're going to go to our load A, and actually it's load 8-bit, as you can see right here. So I'm going to go ahead and click on that. It'll bring up the page for us. And one thing I wanted to show you real quick is we have this table here that breaks everything out for us nicely, and I'll go through this in just a second. But anything that is in white, such as this load A and load B, is for the 6809. Anything that is in gray in this reference guide is for the 6309 only. So anything that you do see that is in gray, we will not be using those. We might be getting into 6309 at some point in the future, but definitely not in this series or not in the immediate future. So we'll focus on anything that's 6809. So here is our table that shows everything broken out into the several different addressing modes that we can use. And as you can see, load A is our first one here. And if we look in our immediate column, we see the opcode of 86. And as you can see here, we have the opcode of 86 in our machine code. So that's telling us that's immediate mode. If we go over to the direct mode, we see that we have an opcode of 96. And if you look down here in our machine code, you can see where this 96 is. And sure enough, this is where we're doing our direct mode. And as you can see, the next statement down, as we anticipated, because 00 is where our direct page is, the compiler again is smart enough to know that we're using direct page mode here, even though we had indicated the leading zeros. So if we look down at the next one, which is our load A memory address 0150, again, this is a different opcode. So if we look into our chart, we can see that in fact that is extended addressing. So that's our B6 here. So that's what those fields mean. And it's a real easy way for us to tell how this is being compiled and what opcode is actually what it's actually compiling to. Now, a couple of the things that's nice about this reference guide, this little segment down here is actually our condition code register. And if you remember from the first episode, our condition code register is broken out into 8 separate bits. And what this actually tells us here is which bits could potentially be and are affected by this particular series of commands. So in our case, we have the N register, or the N bit in our CC register, which is the negative flag. And that could be either set or cleared, depending on what happens with our operand. Same thing with our 0 flag, our 0 bit. And then we also have an overflow, our V bit here, which is always cleared when this is executed. The condition, or the carry flag in our condition code register is not affected by these instructions. And you can see that down here. One other thing to notice in this table is we have these columns here with numbers in them. And what this is actually telling us, the tilde here is actually telling us how many clock cycles are required for this particular mode of addressing. And the next column over with the number sign is telling us how many bytes are required for this opcode to be executed. And if you look in the direct mode and the extended mode, you can see that we have 2 different numbers in the number of cycles required. And Darren explains this at the beginning of the guide. And basically what this means is this first number here is the 6809 or the 6309 running in compatibility mode. And the second number is the 6309 running in native mode. So you can see clearly that running with a 6309 in native mode, you actually can save clock cycles. So not only do you get additional instructions with the 6309 and potential for additional speed, but you also have greater efficiency in a lot of cases. So that's pretty nice. And that's one of the things that, a lot of the folks in the community like about the 6309. So we won't be doing anything with the 6309 again in the near future. So we'll just focus on 6809, and we'll reference this column on the left when we need to. Then the second column over, as I mentioned, is the number of bytes required for that particular mode. So as you can see, if we look back at our machine code, again, the 86, our first instruction here, is telling us that we need 2 bytes. So the first byte is for the opcode, and the second byte is for our operand. And as you can see here, there's definitely 2 bytes being used. If we look at direct mode, typically you will have just the 2 bytes. And as you can see here, we have our 96 opcode, and the 50 is our operand. So we are in fact only using 2 bytes there. However, if we go over to the extended mode, you can see that that requires 3 bytes. And the reason for that is because you have the B6, which is your opcode, and then your 0150, which is your operand. And that is in fact 3 bytes. So you can clearly see if you can get away with using immediate mode or direct mode, if you're able to put data into a specific memory page and use direct mode addressing for referencing that, you can save yourself a clock cycle each time, and you also save yourself a byte each time, which is really nice. So one other thing I did want to mention real quick, you might be asking yourself, all right, why is there more clock cycles required in immediate or direct mode versus immediate mode? I mean, they're both using 2 bytes only, so wouldn't they be the same? And that's not true. The reason why is because in this particular case, immediate mode, we have the data readily available to us, and we're loading this immediately into the A register. However, with direct mode as well as with extended mode, we're needing to fetch in a different memory location, and there's additional clock cycles required to do that. So in this particular case, you're going to see that there's additional clock cycles required, and it's going to create additional clock cycles in your code, and that'll become evident when you're in loops and you're doing things in a repetitive fashion. So if you do have the ability to get away with direct mode or immediate mode, you can be a bit more efficient than going to extended mode. So one other thing I just wanted to show you real quick with this is, if we look at the opcode map, it's a nice reference as well. It shows you the entire opcode instruction set for the 6809 and the 6309. And again, anything in gray is going to be 6309 only. Anything in white is both 6809 and 6309. And actually, one other thing while we're here, just to reference it real quick, we're going to take a look at the store accumulator to memory. And the reason for that is because here you can see, actually we're not using index mode in this, so we'll have to reference this at some other point in the video. But I wanted to show you how the index addressing works as well. But we'll get to that in a future point. Okay, so I'm going to go ahead and close this here. I do want you to grab a copy and take a look at it. We're going to be using this quite a bit moving forward. Okay, so we can go ahead and get rid of these lines from our code. And before moving forward, one other thing I wanted to touch base on is how we're using our number notation in our source code, and in particular in our operand fields here. As you remember from last episode, we have our decimal 69 representation for our character E. We had also indicated that we could use single quotes to use the character itself directly in our code, again with the # prefix here indicating that we're in immediate mode, loading that E directly, or excuse me, immediately into our A register. A couple other notations that we had talked about were the decimal notation as indicated by the 69. If you notice, there's no leading prefix on this outside of that immediate #. And what we could actually do if we really wanted to indicate that we were using decimal is use the ampersand sign. I don't recommend that you do that. However, one, because it's adding to the code, it's we have the 69, we don't need it. But more importantly, because the ampersand is used for hexadecimal notation in disk extended color basic, the ampersand H prefix and I just don't want to create any confusion with that. So it's perfectly fine if you just leave it the decimal number itself. The other one that we had talked about in the previous episode was the $sign, indicating that we were wanting to use hexadecimal notation there. One that we did not talk about, though, is the %sign. The %sign is for binary, and you might be asking yourself, why would you ever want to use binary when you're coding? Well, it makes it extremely easy as a visual to be able to see when you're using logic operators which particular bits are going to be affected in that logic operation. And I use it almost exclusively anytime I'm doing any type of anding or oring or any of those logical operators within my code. See it quite a bit with the CC register and any other registers where you're doing logical operations. And then finally, one other one that you can use is the @ sign, which is used to indicate octal notation. Octal is not widely used anymore. I know it was used quite a bit back in the early days of 8-bit, especially by those who were doing hand coding of machine code. But it's nice for representing numbers with only 3 bits of data. If there are folks in the community that are listening that still use octal or have a good use case example of it in assembly coding, by all means, share in the comments below. Let us know how you're using it. But for the most part, probably won't be using it. Okay, so we'll put this back, and that's pretty much what I wanted to cover on the notation of numbers in our code, and we'll be explaining this in further detail as we get into these further exercises. Okay, so with that cleaned up, one of the other things I wanted to show you is how we're using start and end start in our code. And as I mentioned in the last episode, we put the start label at the very beginning of our code because that's where we want to indicate to the compiler where we want to start compiling and where the code is actually going to start executing from. So one of the things I wanted to do is pull up our compiled code here, and if you take a look here where we have this 4000, again, this is where the code actually starts as indicated by our org 4000 compiler directive that we have here. So if I were to come into my code and change this start to someplace else in my code, I'll go ahead and take it out of there. And I'll bring it down here to where I have the W, where we're loading the A register with decimal 87. And I save that and I compile it. As you can see, it compiles just the same. We still have our code starting at org 4000, ends at hex address 4037. But if I go to execute this, if I dump this to VCC, it's going to have a slight change to it. And as you can see, we're just getting world out now. And the reason for that is because we are actually starting our execution here. Even though this entire code did compile and it starts at 4000, we're not executing until we hit 401E. And what I'm going to do, just to show you that this still works, is I'm going to change where this actually executes. And we can do that by specifying a memory address. And we do that with hexadecimal notation, and H4000. And if I do that, you can see that it actually output. Well, we overwrote that a little bit. So I'll just do it again up here, and H4000. And there you go. So it does work. It is still compiling. We still have the full code there. It's just changing where it's executing. And one other thing that we can do to take a look at this is I'll just pull up hex editor real quick so we can see the hex dump of this. And this is just my floppy disk tools, which I'm continuing to work on, but there is some functionality to it here. So I'm just going to bring my disk image into here. We actually go to the desktop, and our disks are in Cocoa disks, and I can just drag and drop that there. And as you can see, we've got a hex dump of our disk image here, and I can actually double click it and it'll give us a hex dump of the binary itself. So taking a look at this hex dump, what we have is the beginning of it is just a header on the binary file for it to be able to load and execute within this extended color basic, all binary file starting with 0. Then we have a length here, the next 2 bytes of 38 hexadecimal. And here's our start, the 4000. So this is telling where to load it into memory. And then this portion here is all our binary and machine code. And then what we have on the back end is a footer, and all binary files will end with the FF0000. And then these last 2 bytes here are what are actually used to tell this extended color basic where this should execute. And as you can see, we have our execute address of 401E, which if we come down here to our disassembled code is our load A with the W. So that's how this actually is working. Again, you can see here it's start address of 4000, end address of hex 4037, and our executable address of 401E. So what I can do is I can come back in and I'll change a couple things here on the code itself. First, we'll put that back, get the start right back at the beginning. And what I'm going to do this time is I'm going to take off the end here. And if we go ahead and save this and compile it, we'll close this down, compile, and we'll dump right to VCC. What ends up happening is we get this error in VCC, bin file is corrupt or an invalid transfer address. And what's actually happening here is the execution address for this particular binary is outside the bounds of what VCC can handle to execute from. And I believe it's going to indicate that it's trying to execute at memory address 0000. And if we just click OK here, what we can do is we can come into our code or our VCC emulator, excuse me. And again, we'll execute right from 4000, and we can see that our code still works. So what I'll do is I'll go ahead and close this. So we know that the binary loaded, it just couldn't execute properly. So I'll minimize this, and we'll minimize this, and we'll go ahead and do a refresh on this. I'll just drag and drop this back in there, and we'll hit our binary file. And as you can see here, again, our start address is 4000, as indicated by the executable address of 4000 in our emulator. But if we come down here, the last 2 bytes are 0000, and you can see here the executable address is 0000. And of course, nothing is going to execute there because we don't have executable code at that particular point. If we had tried to do that, it would probably lock up or put garbage on the screen. So that is clearly showing the importance of having the start and end addresses on our source code. So there are cases when you won't need it or don't need it, and that is typically when you're trying to compile a portion of code that you're going to be calling from someplace else, or that you're going to use as a subroutine in another piece of code. But those will be few and far in between. For the purpose of our exercises here and the tutorials we're going through, we're going to want to make sure that we include our start and end start there. The same thing would have happened as if I had removed the start here. It would have still compiled the same, but again, the executable address would have been unknown and would have defaulted to 0, and we would have seen the same thing. Okay, so now let's get started on our next portion of code. And what we're going to do for that is we're going to start with a clean slate, and we're going to get going on writing a looping routine for clearing the screen. We're also going to show how you can use a ROM call for doing just the same thing. However, with our own routine, we'll have a lot more flexibility. We can customize it, and we can do a lot more with it than the standard ROM call. So let's go ahead and close this out. And what we're going to do now is we're going to pull up our template for creating a new source file, and this is the same as that we used in the last episode. And what I'm going to do is I'm going to go ahead and indicate that we want to clear the screen with a ROM call. And the way that we do that is we need to call memory address A928. That's where the clear command is located in our ROM. And the way that we do that is with a JSR command. JSR is jump subroutine. And what we're hoping to have happen with this is we jump to this particular address in memory. It does some things for us, and then it returns back from that subroutine. So the JSR will do that for us. So the memory address again is A928. And for those of you that have access to the Unraveled series of Color Basic and Extended Color Basic and Super Extended Color Basic, they're a great reference, and you can actually look up this information in those reference manuals. I believe that they're available on Color Computer Archive, so that might be a good source for those. Okay, so we're going to put a comment here indicating that we're going to clear video screen ROM call to $A928. And I'm going to go ahead and save it here. But before we do that, we want to make sure we have our own RTS in there, return from subroutine, or else it'll just not execute properly. So we'll go ahead and we're going to save this as a new Hello World file. And what I'm going to do is I'm just going to rename it to hello2.asm. And one thing I did want to note here is I will be using 8-character file names for anything that we're writing in our source code. And the reason for that is because the way that our batch file, our script is working, is it'll take that name and actually use that to name the binaries that are being written to disk. And as many of you know, there is an 8-character limit on file names in Disk Extended Color Basic. So if we want to ensure that we're compatible with that, we want to make sure that we're limiting these to 8 characters. I believe the default will be that it truncates it, and that could create issues because if you have names that are very similar, it might overwrite files that you want to keep. Okay, so we went ahead and we saved this, and what we're going to do is we're going to compile this. And it's hello2, and we're going to target VCC, and there we go. We got our clear screen. So that is a very simple, easy way for you to clear a screen. But as I mentioned, it's not going to suit our purpose in the long run because we're going to be using it to do other things. We want to make sure that we have a lot more flexibility, functionality with our particular routine for clearing the screen. So let's go ahead and do that. So I'm going to go ahead and close this, and we'll minimize this, and I'm going to go ahead and just get rid of this here. By all means, use it if you need it in your future code, but I think you'll see as we get coding here that the flexibility that having our own routine to do this gives us much, much more to work with. Now let's write some code. So to begin, let's figure out exactly what we're trying to accomplish. And to do that, I'm going to bring up the video screen overlay that I had used in the previous episode. And what we're trying to do is starting at hexadecimal address 400, going all the way up to memory address 5FF in this bottom right-hand corner here, is fill this entire text screen with a blank space, in this particular case, the green box. So there's 512 bytes here that we're trying to fill with the same character. So to figure out what character we want to use to store in each one of these memory locations, I'm going to bring up this Cocoa character map, which we also created in the last episode. It's just this little 4-line basic program I had written, and you can copy this yourself if you like. So the green space, this one here, is actually, if we count from starting from 0 here in the upper left corner, this at symbol, inverse at symbol, we go from 0 to 31, 32 to 63, 64 to 95, and this one here is actually decimal 96. So what we can do to begin is load our A register with decimal value 96, and that'll be our blank space. I'll put a comment over here to indicate we're loading character blank to A register. Next, we want to start our index register with the beginning of our video memory space. And again, that's hexadecimal value 400. So I'm going to do a load X statement. And again, we're using immediate mode, so we'll do the pound sign. And we'll do hexadecimal 400. And do point X register beginning of video space. Okay, so it looks very similar to how we had done our Hello World app, loading a value into the A register and then starting off our index register X at a particular point. What we want to do now is store the value that's contained in the A register into the memory location at X. And to do that, we use our store A command, and we're doing indexed addressing, which is comma X, but then we also want to increment X each time we store that value in the A register onto the video screen. So we'll do a plus as a post increment to indicate that's exactly what we want to do. So put value A on screen and increment. Okay, so that gets us going, but what we want to do is we want to keep looping through this these steps until we've hit the end of our video screen, which is down here again at hexadecimal 5FF. So what we want to do is we want to put a compare statement in here, and we want to compare our current value of the X register to a certain value. So we do compare X, which is a new statement for us, and we want to do immediate mode again, and the hex value 5FF. Now, at first you would think that this might work, but what's actually going to happen is we're going to hit the end of our video screen, or get close to the end of our video screen, and as we approach 5FF, we're going to go from 5FE. This will store down here, and then we'll do a post increment, and then we'll hit 5FF. So before we write to this last space, we're going to have a compare here that's going to check to see if we're there. What we actually want to do, since we're doing the post increment, is check to see if we're one beyond that, which is hex value of 600. And we'll just put a statement here, comment, are we at end of video screen? So we're doing a check here to see if we're at the end of the video screen, and if we're not there, what we want to do is go back and continue through this loop. So in order to have a point to reference to, we need to put in an instruction label here indicating that this is the point that we want to loop back to. So I'm just going to call it loop, and again, this is just a reference point for our compare and our branch statement, which is another new statement for us to have a spot to go to. And what we want to do is use a branch to see if we are equal, or in our case, if we're not equal to that 600 hexadecimal value. So we'll do branch not equal, which is BNE, to that loop. And again, what this is going to do, see if we have reached the end of our video space, and if we're not there yet, go back up to our loop and do some more. So I'll put a comment there. No, go back to do more. And there we go. That is pretty much about it for doing our clear screen. So let's go ahead and test this just to make sure that it's working. I'll minimize this. We'll bring up our command window. And again, it's asem hello 2, and we target VCC. And sure enough, there we go. We've actually cleared the screen using our own code to do so. So a couple things that I wanted to note about this. The calls that we have, or I should say the call that we used earlier to do jump subroutine to our ROM call, actually goes through a lot more steps than what our code's doing. It's essentially this plus a lot more for doing some command line argument checking and such, and doing some verifications and whatnot. But for our needs, this is much easier, much simpler. But I also wanted to use this loop to show you a couple other things. One of those things is to show you the versatility of this. So we are storing, and we loaded our A register with the decimal value of 96, which is the blank green square. But say like we wanted to, for whatever reason, fill our screen with white lines using semi-graphics. What we could actually do is change this to a different character. And what I'm going to do is I'll change this to C5 hexadecimal, which is representative of a white line in our character set. So I'll go ahead and save this, and we still have VCC running. We'll close that. We'll compile it again, and there you go. We've got white lines instead. Makes it a bit more flexible for anything that we might want to do with clearing our screen, whatever characters we want to clear with. So one other thing that I wanted to show you with this is kind of demonstrate the speed at which our assembly code is running and do a comparison to BASIC. So real quick, what I'm going to pull up here is another VCC window, and I want to show you what the basic code would look like for something like this. So we'll start with 10a is equal to, we'll use our hexadecimal notation again, and in this case we've got C5 loaded there. 20x is equal to and H400, and I'm trying to do it line by line and do it almost exact as we have it in our assembly code. 30, again, the store A is analogous to a poke command, so we do poke, and what we're doing is we're poking memory location X with the value of A, and then we have on the way out, our operand is incrementing. We've got the post increment, so we've got X is equal to X plus 1. And then 40, we have our compare, so that would look like if X is not equal to and H hexadecimal 600, then let's go back to do more, so we go back to 30. So that should be a pretty close approximation of exactly what our assembly code is doing. Do run, and sure enough, you can see it filling with lines. And you can see the speed difference. I mean, it's much different, much faster with the assembly code. One other thing I wanted to do to show you some of the versatility of what we can do with our loop and our clear screen is I wanted to add a little bit of more functionality to it. And I'm just going to add a couple lines, and what we're going to do is create a second loop where we're actually changing the value of A each time we do a full screen fill of our character. So in order to do that, after this branch not equal loop, I'm going to decrement our A value. What this is actually doing, this is inherent addressing. It's just the opcode by itself. There's no operand after it because the operand is built into the opcode itself. We're subtracting the value of 1 from A each time it hits this particular statement. So once we've done this, what I want to do is I want to check to see if our A is actually hit 0, let's first go up here and change this back to FF255. So I'm going to do a compare A to see if our A value has hit 0. And if it has, we'll go back up to start to load A with FF again. Otherwise, if we have not hit 0, then what I want to do is come back up to load X with the start of our video memory space again. So what I'll do is just name this as an outer loop. And we're always going to branch there if we don't hit 0 with our A register. So branch always, BRA, is a new one for us as well. And we'll do branch always to outer loop. Okay, so let's go ahead and save this. We'll close out of this, and I'm going to go ahead and compile and run this directly in VCC. And there we go. You can see just how fast our assembly code is running. It is going through and writing 512 bytes to the video screen each time, and then decrementing A to go through the entire character set, the entire color computer character set. So you can see how quickly machine code actually runs. And this isn't even with the high-speed poke. So, yeah, that's pretty impressive. And again, you can use this in many different ways in your code. If you wanted to do a title screen or just something psychedelic. But go ahead and close this out. Before we move on, I just want to show you real quick how we can make this code that we had just written even a little bit more efficient. So taking a look at these two statements here, these two are actually not needed. And the reason for that is because this decrement A, what's going to happen is each time it hits a 0, we do not need to do a compare. And the reason for that, it's going to automatically loop back to the value of 255 each time. So we can get rid of these two statements here. Just delete those out. And we'll go ahead and compile and execute again. And as you can see, it runs the exact same way. So right off the bat, we are finding ways that we can optimize our code. So you'll find unique little opportunities like this as you become more efficient at assembly coding. Okay, so let's get back to working on our Hello World app. And the next stage here, we're going to actually create a data string in memory, and we're going to iterate through that string to store our Hello World message on our text video screen. So let's go ahead and get rid of this extra statement, these extra statements that we had just put in here. We'll clean this up a little bit before moving forward. And there we go. So to begin our next section of code, as I mentioned, what we're going to be doing is storing string information, text string information into memory, and then referencing that much as we would kind of a data statement, and analogous to what we would do in BASIC. So in order to do that, we're going to introduce a new command. And actually, this isn't technically a, well, it's not at all a 6809 command. It's called FCC, which stands for Form Constant Character. And what this is actually considered as a pseudo-op. So it's not part of your 6809 instruction set. Instead, what it is, it's it's an instruction for the compiler, telling the compiler what we want to do is we want to form a constant character string in memory. And the way that we do that is much like we would a text string in BASIC. We have to have a delimiter to identify that it's a text, and we're going to use a single quote. And what we can do is we can type our hello world and close that with another single quote. Now, you do not have to use the single quote. You can use double quotes if you want. The only rule here is that whatever you start with, you have to end with as well. So you have to keep the same delimiter at the beginning as you do at the end. If you wanted to, you could actually use another letter. You could use the letter A, and that would work as well, but that would probably be very difficult to keep track of. So we're going to use single quotes and write our little hello world text string just like that. The other thing that we need to do with this is we have to have a reference point for this. So we have to tell our code, or we have to have an easy reference point in our code to be able to know where this is actually being stored in memory. And the way that we do that is, again, with an instruction label. And I'm just going to put a label on this called hello world as our hello world string. Okay, there we go. So what I want to do real quick is I'm just going to save and compile this, and we're not going to dump it into VCC because it's not going to do anything just yet beyond what we were already doing for clearing the screen. And I want to show you how this compiles. And as you can see, we have a successful compile, and we come down here and we look at our machine code, and what you see right off the bat is we're starting with our hexadecimal values of our text string in memory. There is no opcode associated with this FCC. As I mentioned, it's a pseudo operand or pseudo operation only for our compiler. Another example of that is our org statement up here. This is another pseudo op that's not part of the 6009 instruction set, and as you can see over here, there's no machine code associated with it. All this is doing is telling the compiler to set the program counter, our PC register 4000, and that's where we begin our compiled code. So all we're doing with this FCC is saying we want to take these this text string, convert it to ASCII values, and store those as bytecode over here, which again is our machine code. So this here, starting at 48, is a ASCII representation of our hello world string. So let's go back to our code, and what we need to do is we have to have a way to reference this hello world string and also iterate through that string. So what I'm going to do is I'm going to load our X register, again our index register, with the value of this memory location. And to do that, we're going to use immediate mode again. And you can use immediate mode with your instruction labels. And in this case, it's our hello world string. And the reason why we're using immediate mode is because this is in reference to a memory address. And if we go back to our output, the actual memory address of this is 4000C hexadecimal. So this memory label, this instruction label here, hello world, is a alias for that memory address. So what we want to do is we want to load X with that memory address. We do not want to load X with what is contained in that memory address, which would be, as we have done in our extended addressing before. So we want to load it with the value of that memory address. And to do that, we're using immediate mode. So that's why we're using the pound sign there. Okay, so let's continue. The next thing that we're going to want to do is point to where we want to have the text string stored on our video space. And to do that, we're currently using our X register. We've used our X register in the past, but we're currently using the X register for where we're referencing our string that's stored in memory. So what we need to do is use a separate register for that. And we're going to introduce the Y register at this point. So we can do load Y, and we've been storing our video, our text on the video screen starting at, we'll pull that up real quick. I believe we're using Hex 500 to put it right in the middle of the screen. So we'll do load Y, immediate mode, hexadecimal 500. Oops. So this will load our Y register with that memory address. Next, what we want to do is we want to load the A register with a first character in our string. And to do that, we'll do load A, and we want to start at the beginning of our X register, or X, where our X register is pointing, and we'll do index addressing for that, and we do come X, and then when we want to increase X each time that we load A with a text string value. So what this is going to do is it's going to load A with what is contained in the memory location of indicated by X. So in this particular case, it's going to load A with this first text character here, this H. And then what we want to do is, after we've loaded A with that value, is we want to do a post increment and increment X on the way out. So we'll go ahead and do that. And then next, what we want to do is we want to store that on our text string, or in our memory location indicated by our Y register. So we'll do a store A, index addressing Y, and then we also want to increment Y, because just as we had done in our previous Hello World application, we want to increment our location on our video screen each time we store a character. So we do a post increment on Y. So each time we go through this, we want to loop back through until we hit a spot that we're done. And where we want to loop to is where we're loading our A register with the value of X. So we're going to create a point here that we'll just call this loop 2. And here what we want to do is branch always to that loop spot. So what this is going to do, again, is it'll take and load A with what is stored in our X memory location, increment X, so we can iterate through our text string, store A onto the video screen, which is indicated starting at hex address 500, and then do a post increment, so we increment our memory location each time. And then this loop statement, it's branch always to loop 2. It'll continue to go through that cycle until we've hit an endpoint. So what we need to do is tell our code we've hit an endpoint. We have to indicate that somehow. Now, one of the easiest ways to do that, well, there's a couple different ways we could approach it. We could count the number of characters that we have in our Hello World string, but that might change. So that's probably not the best way to do it. It's not going to be the most efficient way to do it. So what you need to do is you have to have some sort of a method to do it that is consistent and makes sense. And what I do is I put an end character on my strings to indicate that I've hit that end point. And there's a couple of different ways that we can do that. We can actually include that in the text string itself, and you can pick anything that you like. I typically do an ampersand or an at symbol because I'm not using those too frequently when I'm doing assembly coding on the color computer. So you can include it in the string itself, or another way to do that is you can put it immediately after the string. And to do that, you can just do another pseudo op called form constant byte for indicating that we just want 1 byte of data. And we can just indicate that we can use our last character as an ampersand or as an at symbol again using that. But what I'm going to do is I'm going to go ahead and keep it in the string itself. It's what I'm accustomed to, but it's up to you. There's, again, several different ways to approach this. by all means do what you want with this one. So what we need to do in our code now is a test to see when we've hit that at symbol. And to do that, we need to check after we load our A accumulator register with our string values. So I'm going to insert a line here, and what I want to do is another compare statement. Compare A to see if we've actually hit that at symbol. And the decimal value for the at symbol is, we'll do immediate mode, and it's decimal value of 64. So after we've done our compare, what we need to do is tell our code what we want to do if we've actually hit that value of decimal 64. And what we want to do is we've actually hit the end of our string, so we want to basically tell the computer that we're done. So in order to do that, we do a branch statement, and we'll do branch of equal to our decimal of 64, and we'll just go to a spot in our code where we're done. So I'll put a reference to done, and our done is actually down here at our RTS, so we'll put a label on that, and that should work. So let's go ahead and save this, compile, and it did work. So a couple things here. So we'll go in and change this real quick, but we still are loading FF into our clear screen. So we'll change this back to our 60. We'll save it, compile it again, and look at the results. And it's working, but we've got that infamous black box block again. And as you remember in the last episode, we had to deal with that. And we had to actually manually go in and change that. So before I do that, before I put some code in to check for that, I just wanted to show you some of the versatility with the text string that we just created. So what I can do is come in here, and I can change this text string on the fly, and let's add some more to it. This is my first, well, technically it's our second assembly language program. And if these get too long, what you can actually do is you can split these up, and you can put them on multiple lines, and you can just continue. And the way that you do that is just create another VC or FCC pseudo-op, and we just have our delimiter in there again. Oh, I left it off this last one. So I just added to my string, and we'll go ahead and save this. I'll compile and dump the output to the screen, and as you can see, we have our FCC pseudo-ops that are creating these strings, and again, it's just dumping the raw bytecode, the raw values of our ASCII characters, into our machine code. Starting with this 48, and it continues all the ways down here to 40, which is our at symbol there. So let's go ahead and write this out to VCC, compile it to VCC, and there you go. And as you can see, we've got a bunch of things going on here. So any place that we have a space, we've got the black box, and any other characters that we have that are like this comma here is inversed as well. So there's an easy way to take care of this, and what we have to do is we have to actually reference our Cocoa character font again, and we'll take a look at, we've got the black box again, which is character 32 decimal. We've got our comma here as well, So what you can see is anything that we want to print in your standard uppercase Cocoa character set is from this @ symbol here to this question mark here. So this would be a value of 64 and go up to our question mark here, which is, what is that, 127 maybe? So anything less than this value here of 64, we want to invert it. So an easy way to do that, if you look, this here is 0 and this here is 64. This here would be 1, this would be 65. If we just add the value of 1, or excuse me, the value of 64 to anything that is less than 64, that technically should give us our uppercase character set. So let's go ahead and modify our code to actually do that. And this will be a very simple fix for us. And the way that we do that is we actually come back up here to where we have our compare statement. So we have already got to compare to 64 because we're using our @ symbol for checking to see if we're at the end of our text. We can also use that to see if we're less than that as well. So we've got a branch if equal to done. What we can actually do is add a second branch statement there that will actually, if we hit a value under 64, we want to add 64 to it. So what I'm going to do is add a statement where let's add to our A accumulator the value of 64 for anything that is less than 64. And just before that, I want to do a test to see if we have anything greater than 64, and we want to skip over that add A statement. So I'm just going to create a skip label here. And where we want to skip to is the store A onto our video screen. So real quick, we do our compare A to 64, branch if equal to done, so it'll finish up once we hit our @ symbol to done, but we can also do our check immediately after that, that if we're greater than 64, we're okay, we're in the okay range, to skip over this add A 64, adding 64 to our A accumulator. And we'll skip over and just write it directly to the screen. However, if we're less than 64, to go ahead and add the value decimal 64 to whatever value of our text string is, and that should work. So let's go ahead and test it and see what we've got. And sure enough, that looks good. Actually, one thing I want to check real quick, or change real quick, is we'll add an extra space in here just so it looks properly formatted, and we'll put a couple exclamation points on that. And that'll test our code as well to make sure that it works for our exclamation points. So let's go ahead and assemble it. And there we go. Beautiful. This is my second assembly language program. So to recap, let's bring this back up. We've done quite a few things here. We've created a loop to clear the screen. We've introduced some compare statements and some conditional branch instructions to handle those compare statements. We've set up a text string in our memory space and shown how that we can iterate through that using a couple registers, the X register for our actual memory location of our text string and our Y register for iterating through our text video space. And we've actually done quite a bit here. So hopefully you've been able to keep up with this. Hopefully there wasn't too much extraneous information. I wanted to try to provide some additional details, but I think we're probably about an hour in this one. But moving forward, we'll try to keep them a little bit shorter. But just wanted to, say thanks for stopping by. Oh, and one other thing. Got a homework assignment for those folks that have been keeping up. What I want you to try to do is take the code that we've put together here, and I want to have you see if you can clear the screen with a black background and store our text string on the video screen with green lettering on a black background. So think about that one. See if you can come up with a solution. It's going to involve a couple other compare statements, and let's see what you can do. If you do have a solution and you want us to review it in the next episode, please share with us, and you can just either provide a solution in the comments below, or you can email me directly at longbranchnevr@gmail.com, and any submissions we get, we'll take a look at them in the next episode. Okay, folks, that's it for this one. Thanks again for stopping by, and take care from Long Branch Never.